Alright, in this problem we have some water and we've submerged a triangular sheet of metal all the way into the water like this. Why? I don't know. Why does anybody do anything? So we know the density of the water, right? Let's say we know the height and length of this triangle here. And what I want to find is the average force acting on one of the faces of this triangle. So for example, what would the force be pushing in from how you're looking right now, pushing straight into the side? So we're looking for that force on one side. Of course, there's also a force on the other side that cancels it out, but we're looking for the force on one side. So the way we're going to solve this is, first of all, using the fact that pressure is equal to force over area, recognizing that is important, because we should be able to find the water pressure, the pressure on it because it's underwater. And so, in other words, force is equal to pressure times area. The only problem is that pressure, in this case, is going to be, let's say we're finding the gauge pressure, and so the gauge pressure under water is going to be, or under a fluid, is going to be rho g h, where h is how far down something is. Okay, but as you can see, well, we don't just have a point. We have an object that is at various depths. So way down here near the L, that's going to have way more pressure than, say, so this is going to have way more pressure than, say, this, right? So, well, we're going to need an integral, basically, right? Because it's going to be changing as you go deeper. As we go deeper, we get more pressure. So if you suspect an integral, then, well, we definitely need a coordinate axis, and we need to draw a representative piece. So if we're going to be integrating downward, probably, right, because pressure increases downward, then let's call that I'm going to call it the x-axis. Is that weird? I don't know. And then that makes this direction the y-axis, I suppose. Okay, and I want to draw a representative piece and see if I can find the pressure or the force on this piece, right? That would be dF, if I can find dF on this thing. So this guy has a height of dx, right? And it's located down at a distance of x, right? And it's got a length of, well, f of x, right? Or y, whatever a function for y is, we can find its length based on how deep it is. It's x, okay? So one step at a time, we know that dA is equal to dx times f of x, right? This is just the area of a rectangle. I chunked off a little rectangle there, and so it's length times height. What we need before we continue, I guess, is a function. We need to know how long this thing actually is. Okay, well, if you look at this as a line, right, look at the hypotenuse of the triangle here is coming out of the xy origin and going straight out. Well, we know the slope of it, right? If you were to tilt your screen over, might be a better way to think of it, because y would be pointing up, and we would have the slope is L over h of this line. And since it goes through the origin, just using slope-intercept form, we know that the function of this line is y, or f of x, equals the slope L over h times x. And you could also come to the same conclusion using similar triangles in geometry. But that is the function of that line, that is the hypotenuse. And so since I know that, then whatever x I'm at, I can plug into this function to get my f of x. And that gives me the length here of my representative slice. Okay, so then I've figured out that dA is actually dx times L over h of x. So dF is going to be, well, we have the force is pressure times area. So the pressure at that point times the area, the differential little piece of area. And so let's see, dF is, Well, that pressure is, well, rho g h being how deep down you are. In my case, I actually used x as the coordinate that says how deep in the water you are. So it's going to be rho g x, okay, that's the pressure part, times dA, which we determined a second ago was dx L over h times x. Alright, so now we're actually starting to look at something we might be able to integrate. Remember that f is equal to the integral of df, right? And so df is all of this mess right here. I've got two x's, I can make that into an x squared, and I usually like to write the dx at the end. And so we get that f is equal to the integral of rho g x squared L over h times dx. Now rho, g, L, and h, those are all just constants, right? They can be written out in front of the integral. Oh, and this integral, by the way, if it's the pressure, if we're finding the average force on the entire sheet, it should be from an x value of 0, which is up at the top of the water, all the way down to h, right? Capital H is how far down you go. Okay, anyways, I was saying I can write the constants out in front of this integral, so I get rho g L over h times the integral from 0 to h of x squared dx. Well, at least it's an easy integral, right? So, rho g. And integral of that is going to be 1/3 x cubed, right? And I just plug in my limits of integration here. I can take out that 1/3. Zero cubed is 0. And so I've got a h cubed and I've got a divided by h here. So final answer for my force on one side should be that. Wait, did I lose a g? I lost a g right here, sorry. G. Well, it's kind of weird looking, so let's see if it makes sense dimensionally, as in let's look at the units. We should end up with a Newton, right, as a unit. So here for density, we have that density is mass over volume, or kilograms per meter cubed. G, well, we know that's acceleration due to gravity. Acceleration is meters per second squared. L, that's length, is meters. H squared, it'd be meters squared. So let's see, I've got meters, meters squared, meters cubed, so that can get rid of some of these meters. And kilogram meter per second, yes, that is a Newton. Okay, so it looks like a dimensionally valid answer anyways, and unless I made a stupid mistake somewhere, that should be our answer. So we had to set up an integral, not only because we were increasing our depth, right, getting deeper and deeper, which increases pressure, but also the area of our representative piece changed each time we got deeper, right, because, well, it's stretched out over a further distance because I was submerging a triangle in this case. A simpler version of the problem would be submerging just a rectangle, and a slightly more difficult version of the problem would be if you were to submerge only partially the triangle, like so. And it's not that much more difficult, it just makes it a little bit trickier to find the y function, you see, because the line that is the hypotenuse does not go through the origin, so our y function, our f of x, will have a y-intercept in that case. But you should be able to figure it out, I think. Thanks.